Lecture 6.5, Day 1, Partial Fractions. This is Pompey's Pillar National Monument in Montana. It is significant because William Clark stopped here on his return trip east from the Lewis and Clark expedition, climbed to the top of the hill to get a look around. And what's interesting is he carved his name in the side, and there's a staircase where you can actually go up and see carved his name on July 25th, 1806. It's now covered with glass, but it's still there. Suppose we want to integrate 5x minus 3 over x squared minus 2x minus 3. This would be a lot easier if we could rewrite it as two separate terms. So we factor the denominator, and we assume that the two terms will look like this. These are called non-repeating linear factors. You may already know a shortcut for this type of problem. We will get to that in a few minutes. Multiply by the common denominator. Now we've cleared the fractions. Clear the parentheses. And then set like terms equal to each other. So if we collect the x terms, we've got 5x equals ax plus bx. And the non-x terms give us negative 3 equals a minus b times 3. We can divide out the x's on the left-hand equation and rearrange the right-hand equation slightly. Now we have two equations and two unknowns. So we can solve this system of equations. If we put the second equation under the first, then we can add the two equations together and get 8 equals 4b, or 2 equals b. Substituting that back in, we get 5 equals a plus 2, or 3 equals a. So now our integral is the integral of 3 over x minus 3 plus 2 over x plus 1 dx, which becomes 3 ln absolute value of x minus 3 plus 2 ln absolute value of x plus 1 plus c. This technique is called partial fractions. The shortcut for this type of problem is called the Heaviside Method, after English engineer Oliver Heaviside, who lived from 1850 to 1925. He looks very serious in this picture. We multiply by the common denominator, but in this step, we let x equals negative 1, which will make this factor drop out. That gives us negative 8 equals a times 0 plus b times negative 4. That cancels out. We divide by negative 4 and get 2 equals b. Now we let x equals 3 to eliminate this factor. And we get 12 equals a times 4 plus b times 0. That crosses out, and we get 3 equals a. So that just works a little quicker than what we did before, solving two equations and two unknowns. So we get the same answer. Good news! The AP exam only requires non-repeating linear factors. The more complicated methods of partial fractions are good to know, and you might see them in college, but they will not be on the AP exam or on my exam. Having said that, let's do some for fun. We have 6x plus 7 over x plus 2 squared. When we have repeated roots, we must use two terms for partial fractions. So that's equal to a over x plus 2 plus b over x plus 2 squared. We clear the fractions, eliminate the parentheses, and once again we set like terms equal to each other. So we have 6x equals ax and 7 equals 2a plus b. That gives us 6 equals a, plugging that in for a in the other equation. We can solve for b and we get negative 5 equals b. So now our expression becomes 6 over x plus 2 minus 5 over x plus 2 squared. Here's another example. Partial fractions only works if the degree of the numerator is less than the degree of the denominator. If the degree of the numerator is higher than the degree of the denominator, use long division first. So we're going to divide this out. So to get 2x cubed, we have to multiply x squared by 2x. And then we multiply 2x times the divisor, get 2x cubed minus 4x squared minus 6x. When we subtract, we get 5x minus 3, which is our remainder. So we can write that as a fraction. And we get 2x plus 5x minus 3 over x squared minus 2x minus 3. Then we can factor the denominator. And use partial fractions to get our answer. This is from example 1. Here's a challenging example. I have negative 2x plus 4 over x squared plus 1 times x minus 1 squared. This contains an irreducible quadratic factor and repeated root. So when we expand, it would look like this. ax plus b over x squared plus 1 plus c over x minus 1 plus d over x minus 1 squared. We have a first degree numerator. We multiply through by the common denominator to clear the fractions. Then we expand and expand again. Obviously, if we were doing this by hand, we'd have to do it very carefully. Now we need to set like terms equal to each other. First, the x cubed terms. There are no x cubes on the left, so we get 0 equals a plus c. And notice I didn't bother to write down the x cubed. For the x squared terms, We find 4 of those, and we get 0 equals negative 2a plus b minus c plus d. For the x terms, there's 1 on the left and 3 on the right. And finally, the units terms, we get 4 equals b minus c plus d. So now we have 1, 2, 3, 4 equations and 4 unknowns. And we can use matrices to solve this and row operations. So I'm going to add twice row 3 here and subtract row 1. Then I'm going to divide this row by negative 2 and move it up to the second row. Now I add 3 times row 2 here and subtract row 2 there. And finally I add row 3 here. And then divide the last row by 2. So we're partway there because we have our diagonal row of 1s. Now we want to clean it up a little more. We can subtract row 4 there. And subtract row 3 from the top row. And we have our diagonal row of 1s and everything else is 0. So there are our answers, 2, 1, negative 2, 1. So using our original template, we fill in A, B, C, and D. And there's our answer. Now, we could do the same problem on the TI-nspire. The command we'll use is expand. And expand is menu 3, algebra 3, expand. And we can format this either way. We can either format it in the traditional way with fractions, or all on one line with parentheses. Either way we get our answer. Of course, with the TI-nspire, we could just integrate and we wouldn't need partial fractions. So now that we have this technology, there really is no reason to do partial fractions for these long problems, but they do show up occasionally for simpler problems.